So what is ACID all about? A database is said to be ACID compliant if you perform some operations on the database as part of a transaction, and that database always honors certain properties, which are ACID for the transaction, such that the overall focus is on ensuring the integrity of your data is always maintained. So before we go into more details on ACID, let's see what a transaction actually is. So a transaction is basically a single operation, a single read, write, update, or it could be a grouping of logically related operations into a single bundle. So before working with JDBC, I always used to associate PL SQL store procedures with a transaction. So you have this procedure that you create in SQL. It's called transfer. It has two update operations. It removes some amount from account 1 and transfers that same amount to account 2. But this is one way to implement a transaction. You can invoke this procedure from your code or directly go to the SQL workbench and invoke this procedure. Another and most popular implementation of procedures, at least in real life, is with the help of application code. You make use of certain database driver libraries like JDBC or Hibernate. So in this Java code, you have two prepared statements basically doing the same thing, one for each update. So you create the first prepared statement, update the account 1, remove some amount, and then do ps1.execute update. Same thing for account 2, you add in some account and then do ps2.execute update, and then finally you commit your changes. So what do these individual execute updates do? So when you execute this query, ps1.execute update, your database engine actually processes your query and computes the results, but does not push them onto the database. It stores the computations. They are local to the transaction. They are local to you. So only you can see your changes. But when you hit connection.commit, whatever computation results were stored, cached by the database engine, they'll be pushed onto the database. So let's start with atomicity. Atomicity is basically all or none. Either all 10 updates of your transaction are executed or none are. So let's say you execute 5 updates, you simultaneously make changes onto the database, and as you're executing the 6th update, the system shuts down. So now your data is in a corrupted state. You've done partial updates. How do you undo your changes? How do you undo the 5 updates that you've done? So you make use of the write-ahead log, which is stored on the disk. So there's persistence. So before making any direct changes to the database, you'll first make note of the operation on the write-ahead log and only then push it onto the database. So once your system boots back up after a failure, you will already know what operations you've done with the help of the write-ahead log, and then you can undo your changes. So atomicity can be implemented using a write-ahead log. Coming to consistency. Consistency basically ensures that the invariants of the database are always satisfied. Now, what do we mean by an invariant? An invariant is basically a logical proposition or a statement that should always hold true for your database. So let's say you're running a business which deals with inventory. So one invariant, one proposition you can define is that the stock for any item can't ever be negative. The minimum value will be 0. Or let's take another example. You're running a school and you have two tables, student and course. And the student table points to course. It has a foreign key. So one invariant you can define is when you're inserting a new student into the student table, the course associated should exist in the course table. You can't add a random course that you don't know about. So over here, I've mentioned that atomicity is a necessary but not a sufficient condition for consistency. First, let's see how does atomicity help with consistency. Let's go back to your inventory business example, and let's say you're dealing with just one product, which is bananas. And let's assume the initial setting of bananas is 100 quantity. Now you have two tables, one is a supply and the other one is a demand. So initially in supply, you have 100 quantity banana, and now you get a demand for 50 quantity. So what will your transaction do? It will subtract 50 from supply and insert a new record of 50 into the demand. But let's say it subtracted 50 from supply and it didn't insert it into the demand. Let's say your system shuts down in between. Now in this case, your invariant of the database is not satisfied. Your overall supply plus demand for banana should equal 100, but it's not satisfied. But if your database were ACID compliant, or at least guaranteed atomicity, you would never have to face this issue. Your data state would always be consistent. So atomicity over here actually helps ensure consistency. Without atomicity, you can't ensure consistency. So atomicity is a necessary condition, but it's not sufficient. It's not the only requirement to ensure consistency. Why is that? So let's say over here, I update the banana stock to -1. In this case, if this transaction just has one command and this command commits successfully. So this was an atomic operation. So atomicity over here passed, but it's still not consistent. Why? Because it fails the invariant of our database, which is the stock of banana of any product can't be negative. Or take this example. You have student and course and you're inserting a new record over here. And the name is GHI, but the course taken is 5. But 5 does not exist anywhere. This is an invalid foreign reference. So in this case, our operation was atomic in nature. It executed. The entire operation executed. The entire transaction executed. But it's not consistent. It violates the invariance of our database. So how do you enforce consistency? One means is with the help of your application code layer. So if you get an operation, your code should be smart enough to check if that operation violates any of the business rules defined or not. But of course, it's more important to have these validations at the database layer as well. So SQL databases provide you with various constraints like foreign key constraints, primary key constraints, unique constraints, and check constraints as well. So if you perform any operation, before actually committing it, it first checks if it violates any of the constraints. If it does, that operation is discarded. And another way is with the help of triggers. So triggers are these stored functions which are invoked automatically before or after your operation. You can configure that. So this is one trigger which looks at all the updates of your transaction, and if it sees that any update makes the stock negative, it aborts that transaction. Next comes durability. So durability is all about persistence. So once a transaction has been committed, even if you have a power failure or some breakdown, some interruption, when the system is back up, that committed data should be visible again. It should be persisted. And how do you ensure durability? Simple, with the help of a write-ahead log. So we saw that atomicity and durability can be guaranteed with the help of a write-ahead log. Consistency can be enforced with the help of these constraints that you can define in your database, or with the help of triggers, or with the application code itself. So lastly, coming to isolation, which is going to make up the remainder of this video. So isolation basically deals with multiple concurrent transactions. So if you have multiple concurrent transactions, ideally, isolation would like each transaction to have a logical view that it's the only transaction alive. So if there's one transaction executing, it should not worry that there's some other transaction that's going to tamper with the data it's reading. So this tampering of data, that's called a race condition. So race conditions are phenomena that occur when multiple concurrent transactions operate on the same or related data. So when one or more transaction finally commits towards the end, it'll have an incorrect picture of the database state, or it'll have a skewed picture of the database state. So there are multiple race conditions: dirty reads, dirty writes, non-repeatable reads, read-write skews, phantom reads. Now, unlike the A, C, and D properties which need to be strictly enforced, isolation can have some leeway. It all depends on your business requirements. So ideally, isolation would like to have only one transaction running at any point in time. It would not like concurrent transactions, such that no race conditions occur. So because isolation provides us with this leeway, it gives us 4 or 5 levels in increasing order of strictness. So the first level, read uncommitted, is the most lenient, and you'll have almost all of these race conditions prevalent. And the last level, serializable, is the most strict, and you won't have any race conditions over there. Now each level basically builds up on the other. So let's say read committed solves race condition A, then repeatable read builds up on top of read committed. So repeatable read also will solve race condition A, but also solve a new race condition B. Similarly, snapshot isolation will solve A and B, but also solve a new race condition C. Now there's two broad techniques to enforce isolation. One is using pessimistic concurrency control, which makes use of locks. And the other one is optimistic concurrency control, which does not make use of locks. It makes use of versions. So both these techniques have their own pros and cons. We'll get into the differentiating details towards the end after we cover these isolation levels. For this video, I'm going to focus a lot on OCC mechanism. Of course, I'll also cover PCC with each level, but PCC will be a short segment because it's not too complicated to understand. Now, what I won't be doing is to go through all these race conditions at the start and then talk about the isolation levels. What I will be doing instead is introduce each isolation level and gradually talk about the race conditions that it tackles. So we'll gradually cross out each race condition as we talk about the different isolation levels. So that brings us to the first isolation level, which is read uncommitted. So this is the most lenient isolation level. It offers no guarantee against preventing any of the race conditions. So in read uncommitted, you're basically reading uncommitted data. So let's see an example. The initial value of banana is 10, and you have transaction T1, which reduces it by 5. So at this point, the banana quantity is 5. Now T2 also reads what the banana quantity is, and it reads 5. Even though T1 did not commit that data, T2 is still reading 5 because in read uncommitted, you're allowed to read uncommitted data. So T2 thinks that the banana quantity is 5. But T1 is not done yet. T1 further updates the stock of the bananas. It reduces it by 1. So now T1's end goal is to have the final banana state to be banana is 4. But now T2 already did its reading before T1 again changed banana. So T2 thinks it has 5 bananas available and it makes a purchase order for 5. But we know that there's only 4 bananas available after T1 commits it. So this violates the integrity of the data. This again violates consistency in a way. So what would have been ideal was for T2 to wait for T1 to do all its operations, commit, and only then begin reading. So this is an issue with reading uncommitted data. That race condition is called dirty reads. So dirty reads is reading uncommitted data. So reading data that has not yet been committed by the transaction. So one scenario for dirty read is this example over here. T1 does some update. T2 then reads from that update even before the commit happened. But T1's not yet done. T1 wants to make further updates. But T2 does not know about that. T2 made use of its dirty read and operates on that dirty read. So T2 has a skewed picture of the database state. Another scenario for dirty read could be T1 makes this update, T2 reads that update, but then before T1 is able to commit it, T1, that transaction gets aborted. So now T2 again still has a skewed picture of the database state. So when do you actually make use of this isolation level? If your application is read only and does not support writes, this level should be fine. But for real life applications, most databases don't even offer this isolation level to begin with. They straight away start from the next level, which is read committed. So in read committed isolation level, you read only committed data, and the main goal of this level is to prevent dirty reads. So if you recall, there are two broad mechanisms to enforce these isolation levels. One is using pessimistic techniques and the other is using optimistic techniques. In this video, I will be talking about optimistic techniques using MVCC approach, multi-version concurrency control. So for each new update that some transaction does, you're creating a new version of that data. While for pessimistic, when I talk about that, I'll be making use of two-phase locking, reader and writer locks. There are other mechanisms to achieve pessimistic and optimistic techniques. We won't go into that. The most common is using MVCC/2PL. In the description of this video, I'm going to attach a link to a blog that I use as reference when I was studying optimistic techniques using the MVCC approach. It contains sample code for a very dummy database that implements all these 4 or 5 levels. Now, I won't be going through the code in this video, but I'll talk about the broad architectural design that blog references. So you have X, Y, these are the data objects, the data items, and associated with each data object, you have these different versions. So if transaction 1 wants to write something, it creates a new version, writes the value. Over here you have transaction start, which specifies the transaction that created this version. And over here is transaction end, which is what transaction deleted this version. Similarly, if another transaction wants to perform an update to the same data object, you'll be creating a new version and have the same few properties, which is the version's value, the transaction who created it, and the transaction who ultimately deletes it, which will initially be blank. So this is one data structure. You also have another associated data structure, which is the transaction metadata. It'll contain the state of the transaction. Is it in the running state? Is it in the committed state? Is it in the aborted state? And also the read and write sets for each transaction. What do I mean by this? The read set is basically the set of all the data items X, Y, Z that the transaction has touched during its lifetime. The transaction has read during its lifetime. And write set is basically all those data items that you've written into during the transaction lifetime. Why do we need these? We'll see this when we talk about stricter isolation levels like snapshot isolation onwards. Now, this isn't exactly how most real-life database systems will enforce the different isolation levels. You can have your own design on how to have multi-version concurrency control. But this is the diagram that I use as a reference when I was going through that blog. Let's, for the purpose of this video, use this picture as a reference when we talk about our different isolation levels and how to implement them. Okay, so one point that I mentioned about read committed is that you only read committed data, but there is a nuance to it. And it's this point. In all isolation levels, you always consider updates or deletes that you as a transaction have made. So let's take this example over here. T1 sets X is 5. Now T2 overrides that, or basically creates a new version, a new node, sets X is 10 and commits that. Now you are T1. Now when you're performing the next read, will you consider X is 10? It might seem so because read committed reads only committed data. But again, make note of this point. In all isolation levels, your updates, your deletes will hold precedence against everyone else. So T1 will actually read X is 5. So in read committed, you only read either your local writes or committed writes from some other transactions. If there are committed writes from other transactions, but you also have your own writes, your writes will take precedence. Now this makes sense when you think about it rationally. There's no need to by heart these 2 points. If you were to create your own transaction and you make an update to some data item, and then a few operations down, you read from that same data item, obviously you'd expect to read that same item value that you set it to. No database system would want anything else. Even if in between reading some other transaction made its own commit, you would still expect your own local write to win, because at the end of the day, in the grand scheme of things, isolation wants to make sure that you are the only transaction that's running. So you don't want to get a skewed picture because of someone else. So your local writes, your local updates wins over committed writes from some other transactions. So the way this might have been implemented using this picture as a reference is that initially T1 sets X is 5 over here, value X is 5 by T1. And then you have T2 which sets X is 10, that's a new version. So you have X is 10 set by T2. And then T2 commits it. So it stars this version over here. Now, when T1 reads X, it looks at the latest version and it knows it's committed. It might consider it, but T1 also knows that it made its own local update. So this gets precedence over this committed data. If this did not exist, then obviously T1 will read from T2. Let's walk through a couple of more examples to drive home this picture. So you have C1 that begins, C2 that begins, and now C1 does a set X hey. So this is the first node, the first version that comes in, hey with C1. C1 does a get, even though this is not committed, this is a local write, local to C1, so C1 will get hey. Now C2 does get X, but there is nothing committed over here and C2 also has no local write, so C2 will get null. When C1 commits it, this version is starred and C2 does get X again. Now it can read this node. C3 comes, C3 sets its own version X to YOL. So this is a new node, a new version over here. Now when C3 does get X, there is a committed data, but C3 also has its local update, which will get precedence. So it'll read YOL. Now C2 is this old transaction. Now C2 does get X. Does it read hey or does it read YOL? C2 will actually read hey because this newer version is not committed. C2 then does a delete on X. Now what does it delete? It deletes that version which it read, and it read the first one, so it deletes it. It's a local delete, it didn't commit it yet. Now when C2 does a get X, it gets null. Even though it didn't commit it, but this delete was local to C2, hence it gets null. C2 now commits it, and now C4 begins, and C4 tries to get X. So even though this version has been formally deleted and committed by C2, but we know that C3 also added its own node over here. So C4 tries to read from this node, but it sees that this is not committed. And it goes here, it sees that this is deleted and committed. So C4 gets null. C3 then does get X, and it can read this straight away. Let's look at this example. C2 begins, C2 sets the value of X to high, C3 begins, and C3 also sets the value of X to hello. Now C2 does a delete on X. What does it delete? Does it delete this one or does it delete this one? C2 deletes that which it can read. So C2 deletes its local write, but it doesn't commit it yet. Now C3 does a get on X. So C3 can straight away read from its local version. C2 now commits. So this delete is now formally committed. C3 does a get on X. Even though this delete, this X has been deleted and committed, but C3 has performed its local write, and for C3, local writes take precedence, so it'll get hello. Let's take a look at this example. C2 sets X to high, C3 then sets X to hello, and C3 deletes its local version. C2 when it'll get its own local version, which is this one right here, high. C3 now commits, so its local delete is now formal. C4 begins and C4 reads from X. What will C4 get? So you had X high, you had X being hello, and this hello version was deleted and committed. And this is the latest version. So when C4 reads, the read will go to this, the latest version, and it sees it's deleted. So C4 will get null. So let's take a look at the equivalent pessimistic approach to implementing the read committed isolation level. So the first point is you grab read locks when reading and release it immediately after the read statement is done. That makes sense. What about point 2? You grab write locks when you're executing the update operation, but you release it only at the end of the transaction. Now, why is this the case? It is more beneficial in hindsight to just release the write lock after the operation is done, because you know that locks are pretty expensive. The longer the lock is held, it means other transactions will be in the blocking phase. They'll have to keep waiting. So why are we releasing the write locks at the transaction end? So it all has to do with preventing this race condition, which is dirty reads. So let's revisit the same dirty read example with the pessimistic technique. So T1, before making the update, will grab the write lock over that banana record and only then update its value by decrementing it by 5. But it does not release the write lock yet. T2, the concurrent transaction, then try to read the value, but it's unable to fetch the read lock because there's currently a write lock over that particular record. So T1 can proceed with whatever updates it wants to do so, and only at the end of its transaction, when it's committing, will release the write lock. So only when it finally releases the write lock, the value of banana will be finalized, and only then T2 will be able to get the read lock for that record, and then it reads committed data entries for banana. So we saw that to implement the read committed isolation level using pessimistic technique, you grab the read lock at the start of your select query and release it immediately after. If you want to make an update, you grab the write lock at the start of the query, but to prevent dirty reads, you will release the write lock only towards the end of the transaction after you commit. Let's take a look at the final example and end read committed. So C1 does begin, C2 does begin, C1 now does a set X to high, C1 commits it, so this version is starred. C2 then reads from X, so C2 will get high. C3 begins, C3 sets X to hello, so C3 sets X to hello, and C3 then commits it, so this version is also starred. Now C2 does a read of X. Where will it read from? It'll read from the latest version, and this version is also committed. So C2 will now read hello. So C2 initially read X is high, and then after a series of operations again reads the value of X, but this time it's hello. Now, what if your business requirement is this? You read the value of X initially, and based on high, you perform some series of computations. Now you decide to read X again. This time it's a different value. And now you again have to perform some series of computations. But because this is part of the same transaction and the series of computations you're doing are tied to the value of X, it makes sense that whatever computations you're doing should be on the basis of the same X value. So if your business has this sort of requirement where you're reading the value of a data item, performing some computation with that data item's value, and then as part of that same transaction, after some time, you're again reading that data value item and performing some more computation, and you want that data item's value to be same across the multiple reads that you're doing in that transaction, then in that case, a read committed isolation level will not help against it, because it does not guarantee that you'll have a repeatable reads. You have this race condition, non-repeatable reads in read committed. So that brings us to the next isolation level to solve against this particular race condition, non-repeatable reads, and that isolation level is called a repeatable read level. So up until now, we saw two race conditions, dirty reads and non-repeatable reads. Before we go into more details about the repeatable read isolation level, let's take a look back at this example that we discussed when we saw read committed isolations. The issue is we read a certain value, some time progresses, and when we read back that value would have changed. And why would it have changed? Because some other transaction might have updated it and committed it during the lifetime of our transaction, somewhere around here. So let's talk about a possible approach to solving this non-repeatable read problem. And this can also serve as a means to enforce the repeatable read isolation level. So this is my custom approach. Obviously, real life databases will have their own variants. So going back to our architecture for our custom MVCC database, you have the same example for non-repeatable reads. C1 initially sets X to high. So C1 sets X to high, and let's call this version V1. And it also commits it, so it stars it. Now C2 reads from X, so C2 will obviously read high. And if you recall, we also have this transaction metadata, so we can make note that in C2's read set, it read from this data item, which is X, and the value that it read is version V1. C3 now sets X to hello, so you'll have a new node over here, C3 hello, and let's call this version V2, and C3 commits it, so C3 will also star this. Now C2 reads X. Now before blindly looking at the latest version and reading hello, C2 will first take a look at its read set, and C2 sees that, oh, I already made a previous read, and that read was from version V1. So even though this new commit came in between, I will not consider it. So C2 will again just go for this V1 version, and the second instance, C2 again reads high. So repeatable read isolation level builds upon the previous level, which is the read committed level. In this, there is no scope for dirty reads, obviously, and also there's no scope for non-repeatable reads. Over here, like all isolation levels, reads are done for local updates. Definitely, this will have the highest precedence. What if there's no local update and you do a read? Then in that case, you will consider what the latest version is. And for all subsequent reads that you make for that same data item, you're going to consider the same commit that you initially read. This is in spite of there being latest commits after you first read, you will still read the same commit that you first read. Why is this done? So that you will have repeatable reads, you will have consistency across your transaction. Let's take a look at two examples to solidify our understanding of repeatable reads. So here you have C1 that begins, C2 that begins, and C1 does a set X to hey, and C1 does a get. Obviously this is local to C1, so C1 will get hey as output. C2 does get X. This is not committed, so C2 will not get anything, it'll get null. C1 now commits it, so this is solidified over here. C2 now does a get X. Now this version is committed, so C2 will read X's hey, and also in C2's read set, you will make note that you read the version of X. That version is from V1. So let's name this V1. Now C3 begins, C3 will create its own version over here and it'll update it to y'all, and C3 also commits it. So this is solidified. Now C2 again does a get X. So even though this is the latest version, C2 in its read set made note that it initially read from version V1 instead of V2. So for all subsequent reads, C2 is going to again read X's hey. Let's take a look at this final example. C2 does a begin. Now C2 does a set X to high. So let's call this V1. C3 also creates its own version over here. We'll call this V2. This is by C3 and it sets it to hello. Now C2 will delete its version and commit it. So now C3 is doing a get X. When C3 does a get X, obviously this is local to C3, C3 gets this. So to summarize, repeatable read will read only committed data, and it tracks the version or the timestamp of the first time you read a data object. All subsequent reads to that same data item should reference that first version that you read. Let's take a look at the equivalent two-phase locking pessimistic technique to implement repeatable reads. So it's just one point. You grab the read and write locks at the start of your statement when you're reading or writing, but you'll release both read and write locks only at the end of the transaction. So let's take this example. The initial value of X is 10. T1 does a begin, T1 does a read, and T2 then does a begin. T2 overrides the value to X is 50 and T2 commits it. Now T2 reads it and T2 commits it. So T2's read in the second instance will be X is 50. So if you have your read lock over here and you were to give up your read lock at the very start, then in this case your write does its job, it commits, and then when you grab the read lock again and read again, it'll be a non-repeatable read. So two-phase locking to solve non-repeatable reads should have the read lock at the start of the statement and only release the read lock towards the very end over here. So when T1 tries to read X, it gets X is 10. Now when this transaction tries to get the lock, the write lock for X, it can't get it because there's currently a read lock over here. So T1 can proceed, commits, and in this instance also will get X is 10, commits, releases the read lock, and then T2 can proceed. Let's take a look at the next isolation level, which is snapshot isolation. So I've put a star over here because this isolation level is specific only to OCC databases and only to some variants of OCC databases. We'll get into more details later. You won't find this level as a separate level in databases which implement pessimistic concurrency control. Why is that? We'll get into more details. So snapshot isolation is specific only to OCC databases, and that is also implementation dependent. What race condition it aims to solve is this one, read skews. Let's talk about it. Let's understand read skews with the help of this example. So assume you have a database table with 5 records, which stores the person's name along with their account balance. So one invariant of your database can be the overall balance across all the account holders. The total sum that your bank has is $600, and your bank will only have money exchange between individuals. Let's not assume that you have an external bank. So any money transfer will happen only between individuals of your bank. So the overall amount of money that your bank contains is $600 and it sums up to that. So let's say you have a transaction T1 that iterates over all these records and calculates the amount of money that your bank has. So goes over the first record, A has 100, B has 50, it sums to 150, C has 50, it sums to 200. And just as it's about to read D, you have a concurrent transaction T2. Now T2 tries to transfer $50 from B to E. So let it do that. So B will now have $0 and E will now have $350. And T2 commits. T2's job is done. Now we resume with T1. So T1 summed up to $200 so far. As it reads a D, it's going to be $300. Now, as it reads record E, it's going to be $650. And this violates the invariant that we've set for our database. So let's take a look at a couple of formal definitions for reads queues. So a long running transaction can have situations where the value of certain data items changes between when the transaction starts and when the transaction ends. So a reads queue basically occurs when a value that has been previously read by a still ongoing transaction is overwritten by some another transaction and committed. So as the in-flight transaction still progresses reading, it could be the case that when it's committing, when the operation is done, it will have a very skewed picture of the database state. So reads queue basically pertains to two or more rows, and the end outcome is that one transaction will have an inconsistent view of the database. So this violates consistency. Now, reads queues might look very similar to repeatable reads, but there is a very distinct difference. Repeatable reads, basically the transaction reads one data item, let's say data item 1, and then again reads the same data item 1, but this time it finds the value is different. What happens in reads queue is the transaction reads data item D1, and after some time, it does not read data item D1 again. Now it reads data item D2. Now from the time it read D1 to the time it read D2, there could be some other transaction that tinkered with the value of D1, and that as a result could affect the value of D2. There could be some relationship between them, like we saw in this bank transfer example. So now when transaction T1 reads D2, this is the first time it's reading D2. It reads it, and when it commits it, it'll have a very skewed picture of the database state. It'll violate the invariance of our database. Now let's continue with our repeatable read MVCC implementation and talk about reads queues in context of that. So initially A is 100, B is 50, C is 50. You have their initial versions over here. Now T1 reads this version, this is committed. T1 reads this, T1 reads this, and T1 is about to read D. But before that, you have transaction T2, which creates a new version of B, makes it $0, this is V2, and creates a new version of A, this will be $350, and it commits this version. Now T2 is done, so T1 will read D, and T1, when it comes to E, will read this latest version which is committed, 350. So you can see that repeatable reads, when implemented using the MVCC, optimistic concurrency control approach, has reads queues. It does not safeguard against it. Now what about implementing repeatable reads using locking mechanisms, using pessimistic technique? Do you still see this? Let's analyze. So in repeatable reads implemented using pessimistic concurrency control, more specifically using read and write locks, two-phase locking, transaction T1 before reading from A is 100 will grab a read lock over here. B is 50, again grabs a read lock over here, grabs a read lock over here, grabs a read lock over here. Now if you recall, it will release the read and write locks in repeatable read only at the end of the transaction, only after committing. So when transaction 2 comes along and tries to transfer from B to E, it sees that there's a read lock here, so it can't apply its own write lock. So in this case, transaction T2 just has to wait. Once T1 is done reading everything, it releases all the read locks, and now transaction T2 can safely transfer from B to E. So what did you observe from this? You observed that reads queues are not handled in the MVCC, optimistic concurrency control approach, in a repeatable read isolation level. But in the same level, if you implement it using two-phase locking, using pessimistic means, reads queues are handled. Now, are reads queues handled in a read committed approach using pessimistic concurrency control? And the answer is no. So let's see why. So if you recall, in a read committed pessimistic means, you grab the read write locks as you're executing the statement, but you'll release the read lock immediately. You'll only release the write lock towards the end of the transaction. So transaction T1 reads A and immediately releases it. Reads B, immediately releases it. Reads C, immediately releases it. Now you have transaction T2 that comes, wants to update B. There's no read lock here. So it grabs the write lock, makes it 0, and makes this 350, and it's done. Now transaction T1 grabs the read lock here, reads it, grabs the read lock here and reads it. So it gets a skewed picture. So in read committed, using pessimistic means, read skews are not handled. They're only handled from the repeatable read levels onwards. So let's go into the second last isolation level, which is the snapshot isolation level. So this level was introduced solely in optimistic concurrency control contexts. You don't need this if you're implementing pessimistic means. We already saw why. So one of the goals of snapshot isolation is to eliminate read skews. It has another goal. We'll get into it in a bit. So we're going with the same MVCC implementation, the same example that we used for read skews. Now, before transaction T1 comes in and starts executing, logically, it's going to take a snapshot of the database. So the main 2 points over here is you're going to read your local writes and you're only reading those versions whose snapshot you took before you started executing, basically whose commit was done before the transaction started. So along with the node, the value, the transaction who started it, the transaction who deleted it, you can also store a timestamp of when the transaction was committed. So T1 reads A, reads B, reads C, reads D. Now you have T2 that comes in and T2 creates a new version over here, makes this 0. And yes, it commits this. T2 also makes a new version here and it will commit it. Now, when T1 reads E, it's not going to consider this, even though this is committed, but the commit happened during your lifetime, during T1's lifetime. This version was not there when you took the snapshot. Or in short, in implementation wise, if you were to say, the timestamp of V2 is greater than the timestamp when you were born. So T1 will read this value over here. So going back, you're always going to prioritize your local writes. That's the case in all isolation levels. But point number 2, you're only going to read those versions whose commit was done before you were born, before the transaction was started. That is what is meant by snapshot isolation. So using this, read skews are eliminated. So another goal of snapshot isolation is to deal with write conflicts. Now, write conflicts are again only in an optimistic context. The parallel, it's not exactly the same, but the parallel could be thought of as a dirty write. A dirty write is strictly used in a pessimistic context. There is a difference between them. But snapshot isolation deals with write conflicts. So before going to write conflicts, let's see what dirty writes are and how are they handled in a pessimistic means. So let's have a short segment on dirty writes. So as mentioned, they're solely used from a pessimistic context. And what dirty writes are, if you recall, dirty read is basically reading uncommitted data. So dirty write is basically writing on top of uncommitted data. So any overwrites that you do on top of uncommitted data is a dirty write. Take this example. T1 begins, T1 updates the value of X, T2 begins. Now T2 overwrites the value of this uncommitted data X. It makes X is hello. And then there's a commit happening. So whatever T1 added is effectively lost. So that is one of the causes of dirty write. Dirty writes lead to lost updates. So which isolation level in pessimistic means prevents dirty writes? Is it read uncommitted? Certainly not. There are no locks in read uncommitted. Is it read committed? It is read committed. Why is that? Because in read committed, when T1 wants to update, it grabs a write lock. Now when T2 tries to update it as well, T2 is unable to grab the write lock. So T1 will proceed, update X is high, and then T1 will finally commit and release the write lock. So when T2 next wants to update, it updates basically on already committed data, which is fine. So let's talk about write conflicts, which are used in context of MVCC. So one of the goals of snapshot isolation is to prevent read skews, and the other goal is to prevent write conflicts. So let's take this inventory example. The initial value of banana is 10 quantity. C1 and C2 before executing will first take a snapshot of the database state. So they'll know that, okay, banana is there, its initial value is 10, and it'll always read from this value. Even if you have future commits, it'll read the first value that they took when taking the snapshot. So C1 decrements banana's quantity by 5. So we will create that over here, 5 C1. And C1 in parallel, because it reduced the supply by 5, will create a sales order of 5 quantity. and C1 commits it. So this version is starred. C2 also now thinks, it read first time, it thinks the quantity is still 10 and sets the banana quantity to 4. It decrements it by 6. So in parallel, it also creates a sales order of 6 quantity. So this is C2 and C2 will commit. Now in your sales order table, you'll have two records. One having banana 5 quantity, the other is banana 6 quantity. So it sums up to 11. This already violates the invariance of the database. So ideally what we like to happen is before C2 tries to commit, C2 should know that C1 also operated on the same key, which is banana, modified that key and committed it during C2's lifetime. So C2 should basically abort its own commit, because C2 now knows that while C1 and C2 both started with the same picture of the data, which is banana is 10, C1 in between made some changes, modified the banana state and committed itself, but C2 is still operating with the old picture of banana. So C2 at the time of commit should know that, okay, it's operating with an old picture, and in between during its lifetime, someone else made the update on that same data piece and committed it. So C2 should abort itself. So going back to the 2 points we saw when discussing read skews for snapshot isolation, that is read your local writes and read only those versions whose commit was done before the transaction was created. Now in context of write conflicts, there's another point. No transaction A may commit after writing any of the same data key as transaction B did, and B also committed during A's lifetime. So how will you go about implementing write conflict detection in your custom database? So if you recall, in our transaction metadata, we had the transaction state, the read set and the write set. So in C1's write set, you're going to have it wrote into this particular key, banana. Same thing for C2. You will have in its write set, it wrote to banana. Now C1 is already committed, so its state will be committed. And when C2 tries to commit, C2 compares the write sets of all the current transactions, and it sees that the write sets intersect for banana with C1. And then C2 also checks what is the state of C1. Its state is committed. In that case, C2 will self-abort. So C2 will have to be aborted if during the time of commit, it comes to know that some other transaction which is already committed had made changes to the same data item that we made changes to. So we know that repeatable read was introduced to solve the non-repeatable read problem, and snapshot isolation was introduced in an MVCC context to deal with write conflicts and read skews. Now, traditional SQL databases, they offer 4 levels: read uncommitted, read committed, repeatable read, and serializable, because traditional SQL databases which use two-phase locking, they don't have write conflict phenomena. They have dirty writes, which are already handled in this layer. And read skews are also handled in this layer, repeatable read. So what some MVCC database implementations do is they club these two levels together. And after clubbing both these levels, that level together is called repeatable read level. So in some MVCC implementations, repeatable read solves the non-repeatable problem as well as solves dirty writes, write conflicts and read skews. But in other MVCC database implementations, there is a clear difference between these two levels. They offer 5 levels in total: repeatable read and snapshot isolation, which tackle different problems as we saw. Let's talk about the last isolation level and the most strict one. In this, none of the race conditions exist. That's the serializable isolation level. So 2 new race conditions that it tackles is write skews and phantom reads. So let's take a look at that. So if you recall the read skew internal bank transfer example, what happens towards the end is the in-flight transaction reads $650 instead of $600. So towards the end, it'll have an inconsistent state of the database. Similarly, in write skews, the final outcome is that the database will be rendered in an inconsistent state. The invariance of the database will be violated. Let's take a look with this example. So you have 3 doctors over here and their status. And the invariant that you will define is at any point in time, at least 1 doctor will be available. So currently 2 doctors are available, and Dr. Smith and Dr. Jones now both want to go away. So what they'll do concurrently is Dr. Smith's transaction will read the records and check how many doctors are available. Similarly, when Dr. Jones will do the same thing, and they both see that the other person is available. And finally, when it comes time to update and commit, Dr. Smith will mark himself as away, same with Dr. Jones. So finally, the invariants of the database over here are violated because both of them read overlapping data, made some decision based on that, and when they finally decide to write to their respective rows and commit, the invariants of the database are violated. So that's what a write skew is. So write skews occur when two concurrent transactions read overlapping data and write to different rows, but the end outcome violates the invariance of the database. Now, are write skews handled when you talk about snapshot isolation using MVCC? And the answer is no. So let's see why. So you initially have the state of the database as such, Greg is away and the other two are available. And these two transactions will take the snapshot and they both operate on the fact that Greg is away. Now, Dr. Smith and Dr. Jones in parallel will create a new version specific to their record and mark themselves as going away. And they each will commit their own versions. And that's about it. So this honors the properties of snapshot isolation. You're reading only committed data that was committed before you were born, and there's no dirty writes over here because you're writing on your own individual record. You're not overwriting on the same key. So this is where serializable as an isolation level comes into picture. What about write skews being handled in repeatable read using two-phase locking? Does it handle it? And the answer is no. So let's see why. So initially, Dr. Smith and Jones will grab read locks on all entries, and that is fine. Their locks can overlap. You can have read locks from many transactions operating in the same data. That's how read locks work. Now, Dr. Smith and Jones get the idea that Dr. Greg is away, and they both want to make themselves away. So for that, they will grab the write lock on their record and modify that. So the write locks over here are pretty useless. It does not solve a write skew issue because the write locks are on the record specific to Dr. Smith and not to Smith and Jones. So coming to phantom reads, let's take this example. So you have transaction T1, which selects the amount of rows from products where the quantity is greater than 100. Let's say it gets 10 rows. And in between, transaction T2 inserts a new row whose quantity is obviously greater than 100. Now when T1 again executes the same query, this time it's going to get 11 rows instead of 10. So this might seem very similar to non-repeatable read, but there's a difference. So in non-repeatable read, you're reading the same row twice, and in both those instances, you're getting different values. While in phantom reads, you're executing the same query twice, but in both those instances, you're getting different set of rows returned. So that is what a phantom read is. So can phantom read be prevented using snapshot isolation in MVCC? And the answer is yes. Let's see why. So T1 initially executes this. It gets 10 rows. Why is that? Because initially, before executing, it creates a snapshot of the database state and it knows that there are 10 rows whose quantity is greater than 100. Now when T2 comes in between and inserts this Peaches product, it creates a new node, a new version for Peaches and commits it. But when T1 executes the query again, it reads from this snapshot. This is the source of truth. It does not consider this because this commit happened during T1's lifetime, so it discards it. So in both these instances, T1 will get 10 records back. So why did I not talk about phantom reads when introducing snapshot isolation? And the reason for that is because phantom reads are not supported in the repeatable read implementation of two-phase locking. So in two-phase locking, T1 initially grabs the read lock on those 10 rows and reads them out. T2 over here wants to insert something. So there's no concept of read lock here. There's no concept of write lock here. It's a new row. That row does not exist to begin with. So T2 inserts that new row. Now T1, when it again executes the same query, will consider all those 11 rows. It'll grab the read lock on all of them and it's able to read. Now this satisfies our repeatable read isolation properties using two-phase locking. So we need some special approach to deal with phantom reads in serializable isolation for pessimistic control. So before going into the two-phase locking implementation for serializable level, let's first take a look at the MVCC approach for the serializable level, specifically to deal with the write skew issue. So if you recall, read skews is solved by the repeatable read isolation level, and it basically contains one point. That is, if you have a transaction that writes on some data and another transaction is also there that writes on the same data, and let's say transaction B updated the data and committed it. Now when transaction A tries to commit that, it sees that the write sets overlap on the basis of the key and it self-aborts. So basically, if this is transaction A's write set, let's say it's P, the data item that it tries to write into, and this is transaction B, whose write set also has P, and B is already committed. So A at the time of commit sees that their write sets overlap on the basis of this key, and A will self-abort. Now write skews are obviously going to be stricter in that sense. So obviously the first condition is the read and the write sets should not overlap on the basis of any key. On top of that, what write skews say is, let's say this is transaction A right here and this is transaction B right here. And if this is transaction A's read set, which is P, and over here you have transaction B's write set, which is also P. So what write skew says is, if B has written onto the same data object, let's say P, and committed it during A's lifetime, and then A tries to commit, then A will compare its read set with B's write set and sees that there's the common overlapping key, and A will self-abort. And also the vice versa will hold true. So let's say A were trying to write and B were trying to read. So let's say B already read that data and committed it during A's lifetime. Now when A tries to save the write that it did, it checks its write set with the read set of B and sees that there's P which is overlapping, and it self-aborts. So that's what's mentioned over here. No transaction A should be able to commit after reading an object that is in the write set of some other transaction and has been committed during A's lifetime. And the flip is over here. No transaction should be able to commit after writing an object that is in the read set of the other transaction. Now coming back to this example, the read set for Dr. Smith is going to be all three records, Smith, Jones, and Greg. Same thing for Dr. Jones. But the write set for Dr. Smith is going to be Dr. Smith's own record, which is S. Same for Jones. Now let's say Dr. Jones initially committed, that's fine. And now Dr. Smith is trying to commit its write set. Before doing that, it checks if its write set overlaps with the read set of Dr. Jones. And yes, there is a common key overlap, which is Dr. Smith. So in this case, Dr. Smith will self-abort and redo the transaction. So how do you enforce serializable isolation using two-phase locking? So the main goal over here is to basically safeguard against write skews and phantom reads. So if you recall your phantom read example, you're initially getting 10 records, and then you insert a record which has a quantity greater than 100, and in the second run you get 11 records. And for the write skew example, recall the doctor example. So the invariant should be that you'll have at least one doctor available at all times. So both these doctors read the select star from doctors where status is available query simultaneously. They operate on the same picture, and they both will make themselves go away, violating the invariant of the database. So the way to enforce serializable isolation using two-phase locking is with the help of this concept called predicate locks. So predicate locks is basically you have a lock on a certain predicate, and that predicate could be this condition or this condition right here, status is available. So predicate locks is actually a theoretical concept. There's no such lock called a predicate lock. Like you have read locks, write locks. There doesn't actually exist a predicate lock. But for simplicity's sake and considering a very small dummy database, let us entertain the idea of a predicate lock. So taking the first example, this is for phantom reads. So we get the initial query where quantity is greater than 100. And after getting that query, we can basically create a predicate lock on the condition that quantity, if it's greater than 100, that transaction should not be allowed to proceed. It should wait. So After some time, you have another transaction that tries to insert a record for peaches, and the quantity for peaches is 500. So before this query is allowed to execute, you'll first run this query against a list of predicate locks that you have, and you see that this query, this particular record, matches with this particular predicate lock. Quantity is greater than 100. It meets this criteria. So in that case, because there is a lock on this predicate, there's a lock on this condition, you won't allow this query to proceed. So transaction T2 has to wait. So now down the line, when transaction T1 again uses that select query to select all the rows whose quantity is greater than 100, that transaction get the same number of rows. What about example 2? This is about the right skew example. So initially, the first doctor will execute this query, and now you'll create a predicate lock on this condition, status is available. Now when the other doctor also tries to execute the same query, you'll find that there's already a predicate lock on this condition, status is available. So that doctor can't execute this query. That transaction will have to be put on hold. So this transaction can then go along, mark itself as away, and the other transaction can proceed. Obviously, this is terribly inefficient because you have to scan all the predicate locks for all the incoming queries, and you're better off just locking the entire table. So let's talk about index range locking, which is a practical and a realistic implementation of predicate locking. So index range locking basically assumes that you have an index on one of your predicate keys. So let's take a look at this example before we go into the definition. So assuming that you have this query over here, select star from table, where age is between 30 and less than 45. Now you want to create a predicate lock, and the predicate condition is age is between 30 and 45. And let's assume that you have an index over age. So your data is sorted in this form because you have an index. Now, in order to implement a predicate lock, you will basically make use of this index range locking concept. With the help of this index, you will lock a certain range. And what is that range? That range is basically your predicate condition. So all these rows which are in the range of 30 and 45, you will put a lock. Now, because there is no key where the age is 45, you will look at the upper bound, which is 50, and you lock that as well. Now, how does this prevent phantom reads? So let's say tomorrow you get this query that tries to insert a new record whose age is 44. In that case, you'll iterate over your tree and you'll see that you have a lock in this particular range, and there's no way to fit in that particular record over here. So that transaction will have to wait. Again, this is just a very crude implementation of predicate locking, and there's extremely high chances that no actual database implements predicate locking the way that I describe it. This is just my understanding. That's because predicate locking is very hard to implement for real life scenarios. What if you don't have an index on your predicate condition? In that case, you can't use predicate locking. You can't make use of the BB plus tree. In that case, you're better off just locking the entire table. Another downside to predicate locking is it tends to lock more rows than what is required. So let's say your predicate condition is between 30 and 45, but you don't have 45 over here. So there's no precise locking. So let's say you have your upper bound is 500. So in this case, you're locking entries in the range of 30 to 500. And that's a pretty big range, way more than what is actually needed. So you're better off, again, just locking the entire table. So what is actually seen in most real life cases is if your business requirement is to go for a serializable level, you're just better off implementing it using the MVCC approach. That is way more simplistic, and that's actually more realistic. So here's a quick summary for the MVCC and the two-phased locking implementations. First, going over MVCC. For read uncommitted, it solves nothing. Read committed, dirty reads. Repeatable reads builds on top of read committed. It solves dirty reads and also prevents non-repeatable reads. Snapshot isolation builds up on dirty reads, non-repeatable reads, and also prevents write conflicts, read skews, and phantom reads, as we saw. Serializable prevents write skews plus everything above. When you talk of two-phase locking, read uncommitted prevents nothing. Read committed prevents dirty reads and writes. Repeatable reads prevents everything above, plus non-repeatable reads, obviously, plus also read skews in two-phase locking. There's no snapshot isolation in two-phase locking. There's only a fourth level over here, which is the serializable level. and it prevents everything above plus write skews and phantom reads. So let's end this video with a short segment on OCC versus PCC. So in OCC, obviously there's no locks involved. You have different versions instead, while PCC makes use of shared exclusive locks and variants of it like predicate locks. So how does OCC work? The transactions are able to read or write freely. There's only issues that can arise at the time of commit. If there are issues at commit, you have to check for conflicts. And if there are conflicts, that transaction will have to undo itself. While in PCC, the only hurdle is at the initial stage. Transactions just need to grab the locks. But once they have the locks, then it's game over. Then they can do whatever they want and commit itself. What about blocking? There's no blocking in optimistic control, while in pessimistic control, transactions may be blocked and they'll have to wait for the lock, and that might obviously consume CPU and storage resources. So a downside to OCC is obviously, while initially it's all smooth sailing, you don't have to worry about locks, but at the time of commit, if you detect that there's a conflict, then that transaction, especially if it's a pretty complicated, long-winded transaction, the transaction has to be aborted and it should redo itself. So optimistic control is very useful in low contention environments. If you have multiple transactions, but they don't interfere with each other's data keys, the keys that they operate on are independent. While pessimistic control is obviously better for high contention workloads where you have a lot of writes coming in and those writes can basically touch any key. So in summary, you use optimistic locking when you don't expect most writes to be accessing the same data. And if they do, one of the transactions will get rolled back and retried. And you use pessimistic locking when you expect transactions to access the same data. In the next video, let's talk about serialization and column-oriented storage.